In the last lesson, we learned about logarithmic functions. In this lesson, we're going to learn about properties of logarithms. So different things that we can do to manipulate an equation where that new equation will equal our original equation. We're going to see of different ways that we can rewrite things. So in algebra, you learned some basic properties of how exponents can be added, subtracted, or multiply in order to simplify an equation. So the product property from algebra said that if you have some b raised to the power x times some b raised to the power y, that's the same as b raised to x plus y. The quotient property said if you have b of x over some b of y, this is a b, sorry if that looks like an h. So if you have some b raised to the power x over some b raised to the power y, that's the same as b to the x minus y. The power property said if you have b of x, b raised to the power of x, and that whole thing raised to the power of y, that you ended up with b raised to the power x times y. So those are some important things to keep in mind. The other thing that you need to remember from last time was our basic logarithmic form and our exponential form. These two things are equal to each other. So given log base b of x equals y, we can say for certain that b raised to the power y equals x. B to the y equals x. This is a super important one to remember. And that's when we have log base b of x equals y. So these are interchangeable, but this one is a very, very important one to remember because often you'll be given an equation in logarithmic form and need to use the exponential form in order to determine some things about it. We're going to use this exponential form with these properties, with product property, quotient property, and power property in order to simplify some equations. So when we do this with log, we end up with a new product property, a quotient property, and a power property given that those above equations. So if you're given log base b of x times y, this is the same as log base b of x plus log base b of y. So if you have that multiplication, that product property x, y, you end up with log base b x plus log base b y. If you're given log base b of x divided by y, this is our quotient property, we end up with, in the same way that quotient was before, x minus y. So these are sort of the same thing. Product property, you had multiplication, you end up with an addition. Quotient property, you had division, you end up with a subtraction. And the power property says if you're given some log base b of x raised to the power p, this is the same as p times log base b of x, right? We had a multiplication in our final answer when we had that power. So that's a good way to remember it if you forget. Let's do an example. This is a generic example sort of just to prove why this works. So given m equals log base b of x and n equals log base b of y, and remembering b to the y equals x, we end up with b to the m equals x and b to the n equals y. That's just what we took from everything we know so far. So let's look at how we can manipulate these equations. So if we have log base b of x times y, that is the same as saying if we replace our x and our y, we know for x, for x we had b raised to the power m, for y we had b raised to the power n. So we're just substituting those things in. We get log base b of b to the m times b to the n. That's the same as if we have some base raised to something times base raised to something else. That's that base raised to the addition of those two, so we end up with log base b of b to the m plus n. If you have log base b of b raised to some power, that is equal to just that power. That's from the inverse properties of logarithms that we went over last time. So now we have log base b of x times y is equal to m plus n. Well, what is m? What is n? That's just log base b of x plus log base b of y. M plus n becomes this. So if you're given log base b of x times y, you can rewrite it as log base b of x plus log base b of y. So let's look at another example. So express each logarithm in terms of natural log of 2 and natural log of 3. So we're given natural log of 54, and we want to change this so that we have a natural log of 2 and a natural log of 3. Well, if we want that, we're probably going to have to change what this is a natural log of. So if we had a natural log of 2, that's going to allow us to put it in terms of natural log 2, and a natural log of 3 that's going to allow us to do it in terms of 3. So let's look at how we can make 54 into terms of 2 and 3. Well, 2 times 3 cubed is equal to 54, so we write that. So we have natural log of 2 times 3 cubed. That is equal to, from our product property, natural log of 2 plus natural log of 3 cubed. And then from that power property, this natural log of 3 cubed, whatever we're raising that power to, we can actually just stick out in front and multiply. So we have natural log of 2 plus 3 times the natural log of 3. Let's look at another example. So this says evaluate log base 4 of the 5th root of 64. That seems like a huge mess, right? Let's try to make that simpler. And we're looking to evaluate, so we're trying to find a solution. So since the base of the logarithm is 4, we want to express that 5th root of 64 also as a power of 4. This is going to help us simplify this equation. So log base 4 of the 5th root of 64 is the same as log base 4 of 64 to the 1/5. That's just rewriting that root in power form. Then we can change it so that we are using a power of 4. So 64 is the same as 4 cubed. So we have log base 4 of 4 cubed to the 1/5. We know if we have that exponent outside that we're going to do that multiplication. So we get log base 4 of 4 to the 3/5. And now using the power property of logarithms, we end up with 3/5 times log base 4 of 4. And with the power property of logarithms, we also know, if you remember, b to the y equals x, right? Right here we have a b equals 4 and an x equals 4. So what power up here, y, are we going to get? Well, that's just going to be 1. So now we have this part equal to 1, log base 4 of 4, just as the same as 1. So we have 3/5 times 1. That's your answer. Your answer is 3/5. To this big, long, crazy thing, you just get the number 3/5. So there's another formula we should know and be familiar with for properties of logarithms. This is the change of base formula. So for any positive real numbers, positive is important, real is important, a, b, and x, and where a and b are both not equal to 1, we get the equation log base b of x is the same as log base a of x over log base a of b. And this a is just some positive real number that is not equal to 1. So that's all it is. You can use log base 20, you could use log base 100 million, anything will work. It ends up with log base a of x and then divided by log base a of b. That b was your base before. So again, this works for any base a that satisfies the above, but it simplifies with ease for a base a equal to base 10 or base e, and that base e again we call the natural log, written as ln. So base 10, if you remember, we just left that out. If we had a log base 10, we wrote something like log 5. That's saying the same as log base 10 down here. We just don't even need to write that part. So this is when we're going to use this change of base formula. It simplifies a lot for log base 10 and natural log. It gives us an easier way to solve it. So if we were to evaluate this logarithm, log base 3 of 5, that is the same as saying natural log of 5 divided by the natural log of 3. We can just pick a new base, like natural log is base e, and we now have whatever we had as our base in the denominator, and then we have the other number, our log base of, whatever that of was, in our numerator. And if you type natural log of 5 divided by natural log of 3 in your calculator, you're going to get 1.47. So that's another way to solve this, to simplify.